So today we want to talk about the new chapter, which is about the first and the second chapter. The previous chapter is about the convergent sequence. Okay. Then we want to talk about the continuous functions. So the idea is, how do we define a continuous function? We have many ways to define a continuous function. In this textbook, we want to use the idea from the convergent sequence to define a continuous function. Okay. So you may have some learn some epsilon delta definition for the continuous function in the calculus. Maybe some instructors will skip this definition, but anyway, the epsilon delta language will be described in the later section, which is in the section 3.4. However, we will start from the using the convergent sequence to define a continuous function. Okay, so this is the section 3.1. Okay. 3.1, which is about the continuity. Okay. So now let's look at the definition for the continuous function. There are many definitions, but this is one definition. Okay, we say a function f, a function f, which is from its domain D. D is real numbers, a set of real numbers. Okay, D to real numbers. Okay, D to R. D is called the domain, right? The domain of this function f. This function is said to be continuous at the point x0 in D if, so this I just highlight. What's the definition for? The definition is said to be continuous at the point x0 if whenever sequence xn, whenever this one is a sequence in D that converges that converges to x0. Whenever you have this kind of sequence, okay, a sequence in D, and this sequence, the sequence xn will converge to this x0. Okay, will converge to this x0. If whenever you have this one, the sequence which is formed by f of xn, right? For the different xn, you will have different f values. So the f values will for this kind of sequence of xn will form another sequence numbers, right? And this number is called f of xn. And this sequence converges to f of x0. Then we say this one is continuous. Okay, so whenever you have a sequence, when you have a sequence xn in the domain D, okay, this sequence has the limit x0. If the sequence of formed by f of xn, this sequence also converges to f of x naught, then we say this function f is continuous at x naught. Okay, so we use this definition is most students should be new to this definition. This definition you never seen before. This definition is from the point of the convergence of a sequence. Okay, convergent sequence, not from other views. So it's from the convergence sequence. Okay, so we use a convergent sequence. So this is the sequence. This is also a sequence, right? This sequence approaches have the limit, which is f of x naught. Then we say this one is continuous at x naught. So this one thing you should be careful that this xn should be, this sequence xn should be arbitrary. Arbitrary sequence where that converges to x naught. Okay, you have many sequences, right? You cannot not see, okay, if you want to prove some function is continuous, you cannot say, I just give a specific example of xn converged to x naught. You cannot give a specific example. You should say, okay, there exists, okay, for any sequence that converges to x naught, okay? Every sequence xn to converge to x naught. So that is the general thing you need to know when you prove a function is a continuous function. Okay. So this is said it's continuous at x naught. Okay, then if f is continuous at every point in D. So this is just one point, okay? If every point in D are continuous, then we say f is continuous in D. Okay. So another definition, equivalent definition, we will discuss in the using the epsilon delta language, which we will discuss in the 3.4. Okay. So, but in this here, so far we just use this definition. Okay, this is the formal definition. So remark. So we say a function is continuous at x naught. So if this limit, the sequence of f of xn will have the limit and approaches infinity is equal to f of x naught, right? This is also the symbol to denote this function is continuous. If xn approaches x naught. Okay, if fxn equals, okay, we see, okay, sorry, I should say, yeah, it's the same. Now this function f is continuous, right? F is continuous, so you have this one. Okay, so now let's look at example. Okay, proof. We want to prove that this function f of x equals x squared minus 2x plus 4 is continuous in R. Okay. So this is the polynomial, right? So how to prove it? We use the definition. So since it's continuous in R, so that means everywhere, every point, every value in R, right? So we just pick an arbitrary point, okay? Proof that x naught is any point belongs to R, so any point, okay? And xn be a sequence that converges to x naught. Okay, so you see that when we prove something, we need to consider the general case. Okay, you cannot specify what is the xn. Okay, if you want to prove this statement is true. Okay, if you want to prove this statement, you need to use the general sequence. You cannot specify give me a special sequence for the xn, because that is only true for that sequence, not true for every sequence, right? So this is a very common mistake many students will make. They always take some specific sequence. When should we use a specific sequence? That means if the problem asks you to give you some counterexamples, then you can use the specific one. Okay, if you can show that that is not true, this statement is not true, not for every. So you just give us a specific example to prove it. Okay, if you want to show, okay, it's true for everyone, everything. So you need to give a very general sequence. Okay. So we consider this one, right? So now let's look at the limit of this sequence f of xn. What is that? This is the limit n approaches infinity of, if you plug in xn squared minus 2xn plus 4, right? We can use the what? We can use the sum and the product properties for the sequence. All right, this is the sequence, right? We can use the sum and the product properties, right? So you can separate. Okay, and then we know that this one is equal to x naught squared, right? Minus 2x naught plus 4. What's that? That is exact equal to fx naught. All right, so we start from the very general sequence, xn, right? Then we find the limit for this sequence, which is f of xn. And we notice that that sequence has a limit, which is f of x naught. So that is exact the definition of the continuous at x naught, right? So you should have one more sentence. So that tells you that, so f is continuous at x naught only, right? However, since x naught is arbitrary, we didn't give any requirements on the x naught, right? Any conditions on x naught. We just say x naught would be any number in the R. So since this x naught is arbitrary, so f is continuous at every point in R. So that means f is continuous in R. Okay, you should have one more sentence because this part it just show you it's continuous at x naught. Then you need to state that the x naught is arbitrary number. So it should be continuous at any point in R. So it's continuous in R. Okay, so this is the proof. Okay, so now let's look at another example. This is let's define a function f, which is from R to R, by the following way. F of x equals 1 if x is greater than or equal to 0. X f of x equals 2 if x is less than 0. Okay. Then we want to show that f is continuous at every point except 0. So it's continuous everywhere except 0. This is the thing we want to show. Okay. So before that, let's draw the graph to help you to understand. So let's draw the graph. Greater than equal to 0. This is 0, right? Equal to 1. 1 is here. So this is solid point. Less than 0 equals 2. So this is 1. This is 2. Less than, so here is hollow the circle. Right? Okay, so this is the graph. So the first thing is we want to show that it's not continuous at 0. So in other words, if you can find a sequence which converges to 0, then f of that sequence is not converted to f of 0, right? Then we're done, right? Because if you, continuous means for everyone, right? For every sequence. But if you want to show something is not continuous, you just give me a specific number. It's 0. And if you can find at least one sequence which will not have this property, then we're done, right? For not 0. Okay. So now let's prove it. Prove. So for the first case, that x not equal 0. Okay. Then we take a sequence. Which is -1 over n. We note that this sequence, -1 over n, this sequence has the limit will converge to 0, right? Okay, so we find the sequence and it's converged to 0. But f of x of -n, which is what? F of -1 over n. So -1 over n is a negative number, right? N is from 1, 2, 3, 4, 5. So it should be negative number, so it's equal to 2, right? It's equal to 2. So this one is always be 2. So it will not converge to f of 0. What is f of 0? F of 0 from the graph, it's equal to 1, right? And when x equals 0, it's equal to 1. So we find a sequence which will converge to 0. However, f of that sequence, we generate a new sequence, right? The new sequence is a set of number 2, right? 2, 2, 2, 2, 2. Everywhere is 2. So this new sequence has no limit 1, right? 1 is f of 0. It will not converge to f of 0. So by the definition of the continuity, so this f is not continuous at 0. Okay. So this is the way we prove a function is not continuous at a certain point. You just need to figure out what is a specific sequence, right? If you want to prove it's continuous at a certain point, you need to look at using the general sequence. Okay, so now let's let's look at the second case, right? This is just saying, okay, it's not continuous at 0. Now we want to prove it's continuous everywhere except 0, okay, other places. So the next part is that x naught is not equal to 0. And since we want to prove this one is continuous, we need to use a general sequence that this one be a sequence that converges to x naught. Converges to x naught. Okay. Okay. So keep in mind x naught is somewhere, right? Except 0, right? Except 0. For example, x naught is here, right? Except 0. So we have this, if this is x naught, we have xn, okay? Xn approaches this x naught. So that means when n is large enough, it should be around this point, right? So if x naught is here, it should be around when n is large enough, okay? So the f values at these points should be the constant 2 or the constant 1, right? Okay, and it's equal to f of x naught. F of x naught is here, so it's equal to 2, right? F of x naught equals 2. So when n is large enough, so this xn should be around this x naught, which would be on the left side of 0, right? So it also takes the value 2. If x naught is here, so when n is large enough, since xn approaches x naught, that means when n is large enough, xn would be very close to x naught. So maybe here, right? Maybe in this interval, right? Or maybe smaller interval, doesn't matter. It should be around this x naught. So they will take the same value as here. Here is 1, right? Here, all the points around it would be 1. Okay, so this is the basic idea. Okay, so now let's look at, so we let x naught is not 0. Okay, and we don't care about its positive or negative. We just say it's not 0. Xn be a sequence which will converge to x naught. Okay, so then there exists a capital N, right, greater than 0, such that f of xn is equal to f of x naught for n is greater than capital N. Right? This is just this sentence is just the description for my previous one, right? I described this sentence here, right? They share the same values because this depends on how we define this function, right? So when n is large enough, there is a capital N. When n is greater than that capital N, all the function values have the same value as f of x naught. Okay. So here, f of x naught. So the limit n approaches infinity of f of x naught, n, sorry, is equal to f of x naught, right? Because everyone is the same value, so you take the limit. So the limit means n is large enough, right? N is large enough, it's always be f x naught, so the limit is also f of x naught. Therefore, this f is continuous at x naught, which is not equal to 0. Okay, so we finish the proof. Okay, so now let's look at another interesting example. And this example, you should, I cannot say memorize it, but you should know that, okay? Maybe later, many counterexamples will be very, you can use this one as a counterexample, okay? It's a very special example, which is called the Dirichlet function. Dirichlet function. So how do we define this one? This is the function from R to R, real number to real number. But how do we define it? It's equal to 1 if x is rational numbers. It's equal to 0 if x is irrational number. Okay, you can imagine it, but we cannot visualize it. Right? It's almost, it's equal to rational number, then it's equal to 1, but the irrational number is equal to 0. So almost everywhere 0, almost everywhere is 0, 1, right? Okay, so you cannot draw it, but you can think about it. So irrational number, 0, rational number equals 1. Okay. So I would say this function is discontinuous or not continuous. Discontinuous means not continuous, okay? Discontinuous. Sorry. Continuous in R. So in other words, discontinuous in every point. Okay. So we want to prove a function is discontinuous or not continuous at every point. So we just pick an arbitrary point, right? Then say, okay, if we can find a specific sequence, which has the limit of this point, but the f values of the specific limit, specific sequence will not be the f values at that point. Okay, so this is the idea. So the proof is very, yeah, it's very useful proof. Proof. So the first thing, so since x could be any number in R, okay? So now let's separate x, the category of the x values, x naught. So let's let x naught be a rational number. Rational numbers. Okay. The second case would be x naught would be irrational numbers. But you can use the similar way to prove the second case. Okay, we just consider the first case, then we say, okay, similar to x naught to be a rational number, irrational number. Okay, so since x naught, so we want to give us a specific sequence. Okay. So since irrationals, so since this x naught is rational, so we need to play around for the irrational numbers, right? This is the first idea. Since irrationals are dense, right? This we have learned when we talk about the set, right? Irrationals are dense in R, right? Then there exists Vn, okay? You can take Vn to be what? To be x naught plus square root 2 over n. But anyway, you don't need that, okay? Okay, sorry, I just, we can erase it. We don't need it. So this is just an example to help you to understand. We can always find one, okay? There exists, we know that since it's dense, right? We have the theorem guarantee that we have the result when we study that section, right? For the sets. And we know if you have irrational is dense in R. So that means for any point in R, you can always find a sequence of irrationals to approach it, right? Okay, so since this is V, so there exists a sequence which is a sequence of irrational numbers. Sequence of irrational numbers. Irrationals. That is converges to this x naught, although this x naught is a rational number, right? We have this kind of problem in your homework, right? You have a rational number, you must have some irrationals approach it, right? The true or false problem, I remember there is a one, right? Okay. However, what is f of, f of Vn equals what? F of Vn is what? Is a irrationals. Vn equals what? Irrationals would be 0, right? So this is 0. It will not converge to f of x naught. X naught is what? X naught is a rational number. So it's equal to 1. Okay. So that means from this way, okay, so here is some student, okay, may worry about if this one exists or not. Okay, so here I just erase that. This is the example. This Vn, you can take Vn to be, okay, x naught plus, x naught is a rational number plus square root 2 over n. Right, this is the irrational number. Square root 2 is irrational, right? You divide it by n is also irrational. Plus irrational is still irrational, right? Okay. So it doesn't matter. You don't need to give me the specific number, but you say, okay, there exists one, right? Because you have theorem to guarantee that. Okay, so that means f is discontinuous at rational numbers. Rational. At rationals. Discontinuous at rational. In a similar way, similar for the case, similarly for the case that x naught being a irrational number. So what's the similar way means? Because you can use the very similar way, okay, like here. So if x naught is irrationals, so since rationals, so you just change the opposite way, okay? Since rationals is since rationals are dense in R, so there exists a Vn, okay, we can use Un, a sequence of rationals converted to this irrational number. But the f values of this rationals is equal to 1. It's not converted to f of x naught, which is equal to 0. So this f is discontinuous at irrationals. Almost the same, just change the word, right? Change the opposite way. So this is called a similar way. Okay, when we talk about the similar way, we just change it a little bit. Okay, use the same idea. Okay, so this is 1. So now we have the next theorem. .4. So suppose f is a continuous function from R to D, and g is also a function from R to D. Both functions are continuous at x0 in D. Then this function f plus g is also from D to R, right? This function is continuous at x0. 2, f times g, which is also a function from R to 0, to D to R, is continuous at x0. 3, if g of x is not equal to 0 for any x in D, then f of g which is from D to R, this function is continuous at x0. So this is the results we already know. Okay, sum, product, and the division to form a new continuous, will form a new continuous function. Okay. So let's look at the proof. So since we use the sequence to prove quite easy, so we just say, okay, proof. So we need to consider a very general case, okay? So prove that we let a very general sequence xn be a sequence in D that converges to x0. Then that means since f is converges at x0, so the limit n approaches infinity of f of xn is equal to f of x0. If you have this result, that means f is continuous, right? And the limit n approaches infinity of g of x0, g of xn is equal to g of x0. Okay, so now let's prove the first one, f plus g. So we need to look at f plus g of xn. Okay, so if we take the limit n approaches infinity, right? We want to say if this one equal to f plus g of x0. Okay, so this one, so we just separate. This is equal to f of xn. This is the definition of f plus g. When we learn the basic algebra, okay? So f plus g means f of xn plus g of xn. Then you can take the limit for each one because each one has a limit. Each sequence, right? This is the sequence. This is another sequence, right? We just know this one is equal to f of x0 plus g of x0. What's that? This is f plus g of x0. Okay, then we show that, okay, x0, xn approaches x0, then f plus g of x0 at xn will approach f plus g x0. So it's continuous, right? So this is the first part. The second part is the same. We still consider the limit of this sequence, f times g of x0, xn. So that means the limit n approaches infinity. What is f times g of f and xn? That is f of xn times g of xn. Right? Then we take the limit for each one times the limit so this is f of x0 times g of x0. So it means f times g of x0. Okay, the same way for the third one. We consider the limit and approaches infinity of f over g of xn. So that means the limit n approaches infinity of fxn over g of xn. So we take the limit for each one because the limit for each one exists, right? We can only do that for the limit for each one exists. Otherwise, you cannot take the limit for each one. Gxn. And this is f of x0 over g of x0. So that means f of g of x0. F over g of x0. Okay. Okay, so this is the proof for this one. And then we have the next corollary. Okay. .5. So we let P, which is from R to R, G, and G is also a Q, sorry, not G. Q, also a function from R to R. These P and Q be polynomials. Okay, so why we call it corollary, that means you can derive this result directly from the previous theorem. Okay, since it's polynomials, we know the polynomial is continuous everywhere, right? You can imagine that you can always prove that because the first example, it tells you that, right? The first example, right? This is a polynomial, right? You can imagine no matter how complicated your polynomial is, you can always use this way to prove it's continuous everywhere, right? Okay, so the polynomial is continuous everywhere, so it satisfies this condition, right? Satisfy the condition here. At a specific point, it's continuous, right? Then we know that from the last result, which is the f over g, okay, it's continuous. So then p over q, which is the function d from the domain d to R. Where is d? D is where d is equal to all the x values such that this q of x is not equal to 0, right? We need to guarantee that the denominator cannot be 0. On this d, this function is continuous. Okay, so we will not prove it because you can just use the result from the, we consider this d, okay? It's from R to R is continuous. Of course, from R to D is also continuous for P and Q, right? Then this P over Q would be from D, also a function from D to R. Then you can use the previous result, right? P over Q should be continuous, okay? This is this result. Now let's look at the next theorem, which is about the composite function. Okay, when we learn the calculus, we also know that a composite of two continuous functions is still continuous function, right? Theorem 3.6. So we let f, which is from D to R, and the G is not from D to R, it's from U to R, such that f of D, its range of f, would be a subset of U. Okay. Suppose f is continuous. So D is the domain, right? At x naught in D. And G is continuous. And we know f of D, the range is in U. So f of x naught is also in U, right? In U. Then the composition G composed with F, G circled F, which is from D to R. This function is continuous at x naught in D. Roughly speaking, that means this theorem tells you that if you have two continuous functions, okay, of course you should satisfy this condition. The range of this f should be inside the domain of G, okay? Then G composed with f would be a continuous function. So now let's prove it. So we start, because we want to prove this one is continuous in D, right? X naught is in D, so we need to start from a very general sequence, which converges to X naught in D, okay? That Xn be a sequence in D that converges to X naught, right? So we need to prove, we want to show that the limit of f, G composed with f, right? Is that G composed with f or f? Yeah, G composed with f. G circle f. We want to show that G circled f of x naught, xn is equal to G circled f of x0. Okay, so this is our aim. Okay. So this is our aim. Just I use another color to box it. Okay. So how to show that? By continuity. By the continuity of f, of the function f. And the limit n approaches infinity of f of xn would be equal to f of x. Right, this is the condition we have. In other words, this sequence converges, right? It will form a sequence. F of xn will form a sequence. X1, f of x1, f of x2, f of x3, right? Form a sequence. So this sequence converges to fx0. So we also know that by the continuity of g at f of x0, right? We know that from the, you look at the theorem, it said, okay, g is continuous at fx0, not x0, okay? G f x0, so we have a sequence which is in D, no, in U, right? The sequence is in U, and this sequence has the limit f of x naught, and G is continuous f of x naught. So that means the limit, the limit of n approaches infinity of G of fxn, okay, G of the sequence converges to fx0, so it's equal to G of fx0. So you treat this one as a sequence, okay, as a sequence. You treat this one as a sequence. So this, you have the sequence converge to fx, converge to this number, and G is continuous at this number. So that means G of that sequence also converge to G of that number, right? Just by definition, I didn't add anything, right? I just used the definition again and again, right? So this is the final result. What's that? That means, in other words, that is the left side is G composed with f of xn, right? This is the definition how we write it. G circle f of xn. That means G of f of xn, right, is equal to the limit, and sorry, there's no limit anymore. It's equal to G composed with f of x naught. Right. The last thing is our result. Okay. So this is our section 3.1. And you have some homeworks for the 3.1. Okay. So the next time we will talk about the extreme value theorem. Okay, you have learned in your calculus, but we want to show. Okay, we want to prove that. Okay, we want to prove that extreme value theorem. Okay, so we stop here. Any questions? Okay, any questions for online students? Okay, if you have no questions.